Good morning and assalamu alaikum to our lecturer UCS551, Mr. Janvin, and everyone. Today, we would like to present for our group project, which is predicting online shopper purchase intention based on session behavior. Now let me introduce my team member. I am Afifa Nurul Asia, with my team member Farid Friz Ikwan bin Aldrin, Ramel bin Hussein, Mohammed Zulhari bin Soj, and EJ Adrian Edison.
Now let me start the presentation with the introduction. In today's e-commerce world, businesses face tough competition to convert visitors into buyers. Although many people visit online stores daily, only a small number actually make a purchase. By analyzing session behavior, like how long users stay, what pages they visit, and if they return, we can better understand their intention to buy. This brings us to our research questions. Can session behavior predict purchases? What user behaviors most influence buying decisions? Which machine learning model gives the best results? Based on that, our objectives are to explore session data and find behavior patterns linked to purchases, to build a predictive model using classification algorithms, and to compare model performance in predicting purchase intention. Online shopping has become a major part of the global economy, largely driven by digital behavior and data. E-commerce platforms now gather large volumes of session data such as page views, clicks, and time spent on a website to understand what users are doing. These insights are useful for improving the user experience, increasing sales, and creating more effective marketing strategies. This study focuses on session-based prediction, which uses a single browsing session to predict whether a user will make a purchase. Unlike traditional methods that rely on demographic or historical data, session-based prediction is more challenging. This is because user sessions are usually short, unpredictable, and only a small number of users end up making a purchase. The problem relates to three important areas: e-commerce analytics, which looks at user behavior to improve websites and sales; behavioral modeling, which studies how people make decisions online; and machine learning, where algorithms are used to predict if a user will buy or not based on their session activity. Solving this problem has practical benefits. It can help increase revenue, improve marketing results, and provide real-time recommendations to users, making their shopping experience more effective and personalized. Several studies have used session data to predict online shopping behavior. The UCI dataset is commonly used, containing features like page views and bounce rates. Soccer et al., 2019, found random forest to be the most accurate and reliable model, especially for noisy data. Mokhtari and Garib, 2021, used SVM and gradient boosting, showing that pre-processing and focusing on behavioral features like time on site improved results. Lee et al., 2022, explored deep learning models like RNNs, which capture complex patterns but require more data and time. Overall, combining strong machine learning techniques with the right features leads to better predictions. For this project, we followed a four-phase methodology to predict whether an online shopper would complete a purchase using session behavior data. We used the online shopper's purchasing intention dataset from the UCI repository, which includes over 12,000 records with various features like time spent on pages, bounce rates, and visitor types. Our target variable was revenue, which indicates if a purchase occurred. In the second phase, we prepared and cleaned the data using RapidMiner. This involved checking for missing values, converting data types, encoding categorical variables, and removing any irrelevant features. In the third phase, we developed three machine learning models: decision tree, logistic regression, and random forest. These were trained using 10-fold cross-validation to ensure reliable results and prevent overfitting. We also fine-tuned the models to improve performance. Finally, in the evaluation phase, we compared the models using metrics like accuracy, precision, recall, F1, score, and AUC. Among the three, the random forest model performed the best overall, making it the most suitable for predicting a shopper's purchasing intention based on session behavior. Moving on to section 4.1, which is data understanding and preparation. In this phase, we started by importing the online shopper's purchasing intention dataset into RapidMiner. This dataset contains over 12,000 user session records with 17 attributes, including both numerical features like bounce rates and page values, and categorical features like month, visitor type, and weekend. To prepare the dataset for modeling, We first selected only the most relevant attributes for our study. These include session behavior data, such as administrative, product-related, bounce rates, exit rates, page values, and, of course, the target variable revenue, which tells us whether a user completed a purchase. Next, we assigned revenue as the label using the set role operator, so that RapidMiner understands this is our target for prediction. Then, we began the pre-processing steps. We used replace missing values to handle any null entries. Even though the dataset was generally clean, we applied discretize by user specification to group values, such as converting page values into low, medium, and high categories. We also grouped visitor type into 2 categories, returning and new. To ensure the data could be used by machine learning models, we used a nominal to numerical operator to convert all categorical variables into numeric form. Finally, we used normalize to scale continuous features like bounce rates and exit rates, which helps improve model accuracy and performance. All of these steps helped us clean and organize the dataset, so it would be ready for the model building phase. Now we're analyzing our dataset to find patterns that influence online shopper purchases. Visualizing the data helps us understand feature distributions, spot outliers, and see how different factors relate to revenue. Online shopping activities. Figure 8 shows online shopping behaviors. Informational activities are most frequent, but administrative tasks are also notably high. Product-related activities show varied user engagement. Page values and revenue. Figure 9 plots page values against revenue. It indicates both true and false revenue occur across all page value categories, meaning revenue isn't solely determined by page value. Bounce rates across page values. Figure 10 illustrates bounce rates across page values. Higher page values are associated with significantly lower and more consistent bounce rates, while lower page values show much higher and more variable bounce rates. Monthly revenue trends. Finally, Figure 11 shows monthly revenue. We see significant spikes in May, November, and March, while other months generally show much lower revenue. This highlights clear seasonal trends. We focused on applying machine learning models to predict whether an online shopper will make a purchase based on their session behavior. All modeling processes were carried out using loading and preparing data. We began by inserting the execute load and prepare data operator into our process, as shown in Figure 12. This operator called a predefined subprocess that handles the full data loading and pre-processing pipeline. The dataset used is the online shopper's purchasing intention dataset, which includes 12,330 records and 17 attributes. The subprocess included 1. Removing missing values. 2. Converting categorical variables, like month, visitor type. 3. Normalizing numerical features, like bounce rates and page values. 4. Setting the revenue attribute as the target label, true equals purchase, false equals no purchase. This preparation ensured that the data was clean, standardized, and ready for modeling. Cross-validation process. Next, we inserted the cross-validation operator, see Figure 13. This is a common evaluation technique used to avoid overfitting and ensure that our model performs well on unseen data. Inside the cross-validation operator, the workflow is divided into 2 parts: training section, where the model learns from the data; testing section, where the trained model is evaluated on test data. Step 3. Applying decision tree. In the training section, we added the decision tree operator, Figure 14. We experimented with different tree settings such as splitting criteria, gain ratio, information gain, Gini index, accuracy, minimum leaf size, and maximum depth, tuned later in experiments. The decision tree algorithm splits the data into smaller parts based on decision rules derived from attributes such as bounce rates, exit rates, and page values. Step 4. Apply the model on test data ***. In the testing section, we added the apply model operator, Figure 15. This takes the model generated from the training data and applies it to the testing data to make predictions. We made sure to connect the model output from training to the apply model input, the testing data input to the apply model's data input. Step 5. Measuring performance. Finally, we added the performance operator, Figure 16, which evaluates the model using key metrics: accuracy, percentage of correct predictions, precision, How many of the predicted positives were correct? Recall. How many of the actual positives were correctly identified? F1. Score. Balance between precision and recall. AUA. Model's ability to distinguish between classes, true/false. These metrics helped us compare different models later on. Additional models in addition to decision tree. We also tested logistic regression, a statistical method for binary classification random forest, an ensemble method using multiple decision trees for more robust predictions. All models were tested using the same data preparation process and evaluation workflow for consistency and fairness. In summary, this stage was critical in building and evaluating machine learning models using real e-commerce session data. By following a structured workflow in RapidMiner, from data preparation to performance evaluation, we were able to test different algorithms and begin identifying which models performed best for predicting online shopper purchase intentions. Next is experimental design. We did 3 experiments to test how different settings affect the model's performance. In Experiment 1, we tested 4 ways for the tree to split the data: gain ratio, information gain, Gini index, and accuracy. In Experiment 2, we used the best method from Experiment 1. We wanted to see how leaf size affects the model. In Experiment 3, we kept the best method and leaf size from earlier. So overall, we tested the best splitting method, the best leaf size, and the best tree depth. These tests helped us build a better and more accurate decision tree model. Next is the different decision tree criteria were tested. Among them, the Gini index, used in DT3, achieved the highest accuracy at 88.79%, making it the best performing criterion. Therefore, for experiments 2 and 3, the criterion was fixed to accuracy to maintain consistency. Now, looking at experiments 2 and 3, we observed that 4 models like DT7, DT8, DT9, and DT10 all achieved the same top accuracy of 88.79%. The most reliable and well-performing models are DT7 to DT10. These results highlight the importance of parameter tuning, such as leaf size and depth, in maximizing model performance.
Let's start with the raw metric analysis. Among the 10 decision tree models, DT3 had the highest performance across all 3 key metrics: accuracy, precision, and recall. It consistently scored above 90% in each, making it a strong and balanced model. DT2 followed closely, with slightly lower precision but the highest recall among all. DT1 also showed stable results with decent scores in all areas. In contrast, models like DT5 and DT6 had a big drop in recall, meaning they missed many actual positive cases. DT7 to DT10 performed the worst overall, with low values in all 3 metrics, suggesting they are not effective or well-tuned. This shows that not all models work equally well, even when using the same algorithm. Now moving to the ranking heat map. Here, each model was ranked from 1 to 10 for accuracy, precision, and recall. DT3 came out on top again with ranks of 10 in accuracy and precision, and 9 in recall, a strong indicator of consistent performance. DT2 also ranked very high, especially with a 10 in recall. Meanwhile, DT5 and DT6 had poor recall rankings, both scoring 1, which shows weakness in identifying positive cases. DT7 to DT10 received the lowest ranks across all metrics, making them the least effective models. This ranking system helps us clearly compare the models and confirms that DT3 is the most reliable choice overall. For this project, we used session-based data to predict if an online shopper will make a purchase. First, we cleaned the data and prepared it by handling missing values, changing text data to numbers, and normalizing values. This step helped improve our model results. Then, we explored the data visually to find patterns. We found that features like page values, bounce rates, and visitor type have a strong effect on whether a user will buy or not. We used machine learning models like decision tree, logistic regression, and random forest. Out of all, decision tree in accuracy and stability. In conclusion, this project shows that with the right data and tools, we can use machine learning to help online businesses understand customer behavior and improve sales. Thank you for your attention.